Alright, Thermochemistry Notes Day 2. Reading a heating curve. The temperature rises quickly when the solid, liquid, or gas is heated. The temperature is a measure of the average kinetic energy in a substance. This is day 1. The higher the specific heat, and this is C, of a substance, the shallower the line on the heating curve, and the stronger the intermolecular forces. That means the higher the enthalpy of change, the longer the phase change time. At a phase change, the temperature of the substance does not change. Does not change. Because all the added energy is used to break apart the intermolecular forces holding the phase together. So if you're melting, going from a solid to liquid, it does not change temperature, and instead all the energy is redirected to change the actual molecule from solid to liquid. All the energy change is potential, not kinetic. Alright, let's take a look at this graph. You have ice here, you have liquid water here, and you have steam here. That tells you that this section up top is a gas, this middle section right here is a liquid, and this bottom section is solid. Alright, and this part right here, this part in blue, you can see that there's a slope. There's a slope. Slope goes up. My best to color that in. There's a slope. And the y-axis, temperature. The x-axis is going to be energy in joules. In joules. And this is in degrees Celsius, temperature. Alright, so if you look here, when there's an increase in slope, there is a change in temperature. So every time you look at this graph, if you're going from point A to point B, and say you're looking at from C here to D here, you're going up, right? That's an increase in temperature. And vice versa, if you're going from D to C, that's a decrease in temperature. And that applies for every single blue line I drew. Now, let's take another line, and this is going to be in purple. And from D to E, there is no slope change. Why could that be? There is no slope change. See, the line is completely flat. And this is because there is no temperature change. This is strictly going from a liquid here, liquid to a gas. And during this, we talked about all the added energy is used to break apart the intermolecular forces. All the added energy is used to break apart the intermolecular forces holding the phase together. So when you go from a liquid to a gas, that means all the energy, you're converting it, making it into from a liquid to a gas. Same for here. Same for this small purple line here. You're going from a solid to a liquid, right? All the energy is being used to convert the molecule from solid to liquid. All right. Let's take a look at some energy values. So if you go from point A here, let's draw in red, point A, point right here, that's A. You go to point B, you're going up. You're increasing kinetic energy. You're moving the temperature. Same for this point C to point D. When you go up, that's an increase in kinetic energy. And let's label this point F. If you go from E to F, that is also an increase in kinetic energy. You're moving up the slope. But if you go from B to C, you're not changing anything. You're changing not the temperature, but you're changing the state of matter. That is a change in increase of potential energy. If you go up, it's increase. If you go down, it's decrease. Same for this point here. If you go from D to E, that is going to be an increase in potential energy. All right. The stronger the intermolecular forces, the longer the phase change takes. That makes sense because the stronger the bonds are in between the molecules, say we have a molecule here and there's a triple bond between them, versus a molecule that has a single bond between it. It's going to take longer to break this three bond one apart compared to one bond molecule. So the stronger the intermolecular forces, the longer the phase change takes. All right. Energy changes without a phase change. Q equals mc delta T, m times c times delta T. We talked about this in day one. M is mass. C is specific heat constant, specific heat. And delta T is change in temperature. And if you forgot, this symbol right here, this symbol is delta, meaning change in. And this, of course, is going to be our heat. Q symbolizes heat. All right, let's try an example. How much heat is required? How much heat, so you don't know Q, you're solving for Q, is required to raise 250 grams of water, 250, that's mass, grams, from 25 degrees Celsius to 100 degrees Celsius. So you're given the value to look for is Q. You have M, you know the C value of H2O, the specific heat of H2O is 4.18 joules per gram times degrees Celsius. And you know that you have two temperature values. Now, you have to calculate delta T. Delta T is the change in temperature, which is temperature final minus temperature initial. In this scenario, you're going from 25 degrees Celsius to 100 degrees Celsius. So this is your temperature initial, this is your temperature final, because that's 100 degrees is where you end. So 100 minus 25 equals 75 degrees Celsius for delta T. You have all your variables now. All you got to do is plug. Q equals mc delta T, mcat, and you multiply them all together. M is 250 grams. C, specific heat constant, 4.18. And temperature, delta T, we calculated that was 75 degrees Celsius. All you got to do is multiply it all across, and it should give you 78,375. Label is heat, so it's joules, and that is your answer. 78,375 joules. All right. Energy change with a phase change. So that was without, and now we're going to do with phase changes. Heat can be absorbed or released during a physical change of state. The heat of vaporization, delta H VAP for vaporization, VAP, vaporization, is the heat required to vaporize 1 gram of a liquid. Delta H VAP, vaporization, is the heat required to vaporize 1 gram. And this is effective when you're doing condensation or vaporization. When you're doing condensation or vaporization, you're going to use delta H VAP. Heat of fusion, delta H FUS, FUS is fusion, is the heat required to melt 1 gram of a solid. When you use the value of delta H, when you're melting or freezing. So when you're melting or freezing, you're going to use delta H FUS for fusion, and when you're condensing or vaporizing, you're going to use delta H VAP, vaporization. There is a separate equation for this. Energy change at a phase change is calculated using the equation Q for heat equals mass times delta H. So we'll label it heat equals mass mass times change in heat of fusion or vaporization. Fusion or vaporization. And it depends on what you're doing with it. All right. And there is no temperature change in this equation. There is no delta T because the temperature remains constant. No delta T. The temperature remains constant at a phase change. So what we said, this was the key point. At the freezing and melting point, use heat of fusion, delta H, V or delta H FUS. And at the boiling and condensation point, you're going to use the heat of vaporization or a delta H VAP. All right, let's do an example at a phase change this time. All right, it asks you how much heat you're solving for Q equals question mark, is needed to change 250 grams mass of liquid water into steam at 100 degrees Celsius. 100 degrees Celsius. And you're changing liquid water into steam, which is a gas. And I told you earlier that the equation for this is going to be Q equals M times delta H. There is no change in temperature because in a phase change, the temperature does not change. So this 100 degrees Celsius is irrelevant to our equation. We have M, and we need to know delta H. We're going from a liquid to a gas, which is vaporization. Vaporization. Therefore, we're going to use the value of delta H VAP. All right, we can set our equation up. New equation, M times delta H VAP is going to be solved. The equation is different. We're going to have to solve in a different way. We need to solve using dimensional analysis. We have 250 grams H2O over 1. And we need to cancel off this grams of H2O. And we can do this by using the molar mass of water, which is 18.02 grams per 1 mole. Grams, let's make this so it gets less complicated, and 1 mole H2O. For every 1 mole of H2O, there is 18.02 grams. All right, we can cancel off this mole, 1 mole H2O. And this is the important part of this, is that for every 1 mole of H2O, we have to apply the delta H VAP. There's going to be 40.7 kilojoules of energy. And we don't want it in kilojoules, we want it in regular joules. So what we're going to do, we're going to cancel it. So every 1 kilojoule has 1,000 joules. That's because kilo is the prefix that means 1,000. So when we multiply everything across, 250 times 40.7 times 1,000, and then click enter on your calculator and divide it by 18.02, you're going to get 564,650 joules. We convert it into joules, so joules of energy. All right. To find the energy changes in the heating curve, you have to add up the heat for each change. Add up the heat for each change. You can't leave out a random change. You have to add all of them up until you calculate the total heat value of that curve. So, if it asks you what is the heat needed to raise 250 grams of water from 25 degrees to 100 degrees Celsius and make it all boil. See, what we did was calculate the two parts, Q1 and Q2 needed in separate questions. So the value of Q1 we calculated was 78,000 Q1. Let's write this down. Q1 equals 78,375 joules. And we know that Q2 is right above. Q2 we calculated as 654,650 joules. And all you have to do, according to this equation, is all you have to do is add it together. So Q1 plus Q2 is going to be equal to the Q total, 78,000 375 plus 564,650 will equal to the Q total value of your answer. And that will give you 600, let's write this a little straight, 643,400 joules. And that is your answer. The heat needed to raise 250 grams of water from that amount of temperature and make it all boil is 643,400 joules. All right, let's take a look at this phase change diagram. This phase change diagram is like one that we went over. All right, so at this point 1 here, let's draw a blue line. Yep, blue line. Hopefully it'll get it work. Yep, blue line at this. There's a slope change. Same for this part right here. So slope change. And this part right here, there's a slope change. All right. And vice versa for this part, there is no temperature change. There's no slope change because the line's flat. So when you look at these graphs, I've told you before that at point 2, where there's no, point 2 and 4, where there's no slope change, it's going to be a change in potential energy. Change in potential energy, PE. Change in potential energy. And for these blue lines, there is a slope change. So it's going to be change in kinetic energy, KE. Change in KE. Change in KE. All right, wonderful. Let's try another example. Practice problem. What quantity of heat is involved in the process of converting 250 grams of steam mass at 110 degrees Celsius to liquid at 57.5 degrees Celsius? And you're looking for the quantity of heat, so you know it's going to be, you're looking for Q. Q equals question mark. All right. So you have to start off by thinking about this question. You're not going just from a liquid to a liquid, right? You're changing temperatures across multiple phases of matter. So you draw yourself a little handy graph and draw a little crude little graph that looks like this, and label this 100 and label this 0. That point is 0. All right. And now you got to think about, where are my points of temperature, right? I'm at 110 degrees Celsius. We can call this 110 degrees Celsius. And you're ending up at 57.5 degrees Celsius. We'll call that approximately 57.5 degrees Celsius. So from this question, you're going from a steam, so you're starting on this 110, you're going down 1 to this point, you're changing the actual state of matter here, and you're going down this as a final. That's 3 steps, which means 3 equations you're going to do. And if we call this part the top Q, Q1, this middle is going to be Q2, and this is going to be Q3. And we can solve this. Q1 is going from 110 to 100 degrees Celsius. So you can calculate the change in temperature already. Delta T. Delta T is final minus initial. Temperature final minus initial. You're starting at 110, but you're ending up at 100. That means your 100 is the final. 100 minus 110 gives you negative 10 degrees Celsius as your delta T. Going from this point, the point from the top 100 degrees Celsius to 57.5 is similar. 57.5 is going to be the final. 100 is the initial, because you're going from this top point here and moving downwards to 57.5 degrees. So then your delta T, change in temperature, is going to be final minus initial, and that is going to give you negative 42.5 degrees in Celsius. All right, we've calculated both our delta T's, so we learned that we can't just convert this answer and take this answer and use that to calculate delta T. We have to write the graph out and figure it out. Q1. Let's solve Q1 first. Q1 has a slope, right? Q1 is going from here down to here. It has a slope, so we can use MC delta T. Mass of water is given 250 grams. C of water. Now there are three values of C. We have C for solid, we have C for liquid, and we have C for gas. We have to look at it closely and figure out what are we using. What is the gas? What is the liquid at right now? It's at steam, which is a gas. That means we have to use this number for gas, 1.9 joules per gram times degrees Celsius. And then we calculated delta T was negative 10 degrees Celsius. And you can simply multiply all that out, and it should give you negative 4,750 joules. Q2. This one is going from this point to this point. There is no temperature, so you have to use delta H, M times delta H. But this we know is vaporization because it's going from a gas to liquid. You have to convert it using dimensional analysis. So you have 250 grams H2O over 1, and then the molar mass of H2O is 18.02 grams over 1 mole of water. And then for every 1 mole of water, we'll write H2O. Mole of H2O, we got to use the delta H VAP conversion factor, which is 40.7 kilojoules. For every 1 mole of water, there is 40.7 kilojoules of energy. Now convert 1 kilojoule to energy to 1,000 joules. That's the conversion factor. 1 kilojoule has 1,000 joules, and all you got to do is multiply all that out. Multiply everything on the top, click enter on your calculator, and divide by everything on the bottom. That should give you a negative value. Remember, you have to put this negative. This negative is important because you're looking at the data given, right? And you're converting from a steam to a liquid. A steam to a liquid will give off energy because it's moving down the scale from a gas to a liquid. And so you're going to have to be using a negative value for this. And you have to remember to put a negative one in because none of the variables, none of the numbers in our equation here using dimensional analysis is going to be negative. So you have to manually put that negative. That's very important. Let's write that in blue. Negative. And when you multiply on the top and divide on the bottom, you should get 564,650 joules. All right, Q3, last one. This is going to be MC delta T, MCAT, because there is a change. We're going from this point here down to this point here. And we know the mass, M, 250, and then C, we have to use the C for where is it at right now. We have to think about where it's at right now. We just converted from a gas to a liquid, so we have to use the liquid value, C liquid, which is 4.18 joules per gram times degrees Celsius. 4.18 joules per gram times degrees Celsius. Then we calculated our delta T earlier, and we have to use this one because it corresponds with this part here. We have to put a negative 42.5 degrees Celsius in. All we do is multiply all of that across, and we end up with negative 444,412.5 joules. All right. So in order to find the value of Q total, we found 3 separate Qs. We have to add them all up, just like we did in the previous practice problems. So Q total equals Q1 plus Q2 plus Q3. And when you add all of these variables up, we have negative 4,750, we have negative 564,650, and we have negative 444,012.5 joules. Add them all up together, and your final answer should be negative 614,162.5 joules. That is the amount of heat involved. And since this is a negative, we know it's exothermic. Why? Because the negative number is saying that the heat is going to be released from the system. So you have a system and you're releasing heat into the atmosphere or the surroundings. So therefore it's a negative and therefore it is an exothermic. All right. Question 2. Calculate the amount of heat needed to convert 96 grams of ice at negative 24 degrees Celsius to water at 28 degrees Celsius. So you know you have ice to water. Ice is a solid, and you know water is a liquid. So you're converting from solid to a liquid. Every single problem like this, we have to draw a graph. Draw a little graph like this, and draw the lines. It doesn't have to be perfectly accurate. You can just draw the lines. 100, and this is 0. And you got to look at where your temperature points are. You're starting at negative 24 degrees below 0, negative 24 degrees Celsius. And you're ending up at 28 degrees Celsius. 28 degrees Celsius. So you have to calculate the temperature change in between, right? So when you're converting, you're going through this point here and this point here. You're ending up from ice to water. So you're going to climb up from here to here at this point right here, move from solid to liquid here, and then take this path upwards to this point right here. Okay? And so the delta T values, change in temperature, we can calculate. Let's start with the top one. Calculate from this point to this point. When we're going upwards, remember, we're going upwards like this from the bottom. We're going upwards. So this is your initial. 0 degrees is the initial, and 28 degrees is the final. So change in temperature is final minus initial. So final 28 minus 0 is 28 degrees Celsius. Same thing for this bottom part here. The change in temperature is final minus initial. You're starting at negative 24, but you're ending at 0. So final 0 minus, but you're minusing a negative because it's a negative temperature. 0 minus 24 will make it a positive. Therefore, it's 24 degrees Celsius positive. We now have all the values, and the C values are given above in the list of equations, so we can convert. Let's start with labeling the Q's. We'll do this bottom Q first, Q1, and then the middle one here can be Q2, and this last one to 28 degrees Celsius can be Q3. Let's start with Q1. Q1 has a slope increase. You're going upwards like this. So what we can do is we can use MC delta T. And MC delta T says that mass is 96. Our C value is in solid, and the solid C value is 2.1. We're going to use 2.1, plug it in, and then the final is the temperature we found, which is 24 degrees Celsius. Multiply all that across, and you get 4,838.4 joules. Let's try Q2. Q2 is going to be this middle part right here. And there is no temperature change. We can use M times delta H. And since this is a solid to liquid, we can use delta H of fusion. We start with 96 grams of water. 96 grams of water, but it's a solid. And then cancel the grams off by using the molar mass of water on your periodic table, 18.02 grams per 1 mole of water. And then for every 1 mole of water, we know that you got to use the conversion factor, the delta H fusion, which is 6.01 kilojoules per mole. And we convert lastly to kilojoules per mole. We know there are 1,000 joules in 1 kilojoule. And we can solve this now by making sure that we multiply all the numbers on top, 96, 6.01, and 1,000, and then clicking enter, and then dividing by everything on the bottom. When we do that, we should get 32,017.8 joules. Last Q, Q3. Q3 is going to be MC delta T because it's going from this point here to this point here, going up. There is a slope change, temperature change. So all we got to do is plug in 96. And since we're now at a liquid, we can use the liquid value of 4.18, and then the delta T value we calculated was 28 degrees Celsius. And multiply all that across, and you can get 11,235.8. Let's write that 5 a little better. 0.8 joules. Alright, so we have 3 joule values, and we've successfully converted from solid to liquid. And all we got to do to find the total Q value, the heat value required, is add up all of the Q values we found. Q1 plus Q2 plus Q3. And when we add all these highlighted values up, we should get 48,092. Let's write that a little better. 48,092 joules. That is the heat required. And because this number is a positive, there's no negative in front of it. It's positive. We can tell that this is going to be endothermic. Endothermic means heat enters the system. And because it's a positive, we know 48,092 joules of energy enter the system to make the ice water from negative 24 degrees Celsius to positive 28 degrees Celsius. And that's it.